Hello.
Hello, hello, hello. Excuse me, guys. We are gonna start in like couple minutes. If you can grab your seats, that'll be helpful. Yeah. Yeah. You want Kenny right now?
Like, if there are any questions or something, then.
Okay.
I can, like, I'll probably pass
Who
the
is
questions.
Kenny? I don't know.
Kenny is one
Oh, okay.
Like on our own dashboard now. So that takes all of our like 1,000 databases and it plots out.
Okay. So yeah, I think we're running a little bit late, so we'll get started. So folks who are eating pizzas, grab those pizzas to your chair, and we can have the session started. All the speakers are here, so yeah. So again, before we start, really thank you so much everyone for coming in. So I'm Sitesh. I'm one of the organizers of Seattle Systems. So there are a lot of organizers here, not all of them, but we have Jeremy, we have Harry. They help me organize stuff as part of the Seattle Systems meetup. So if you are coming here for the first time, we have events once every month as of now, but we'll not have in December, so probably November will be the last one for this year. But we try to make at least one event. So at least that is what the pace has been. So we try to give at least high quality talks so that we build a community in Seattle. So long story, because when I moved to Seattle a couple months ago, at least, no, it's not a couple months anymore, it's a year now. So I moved to Seattle last year, July. So the only hesitation I had was because there was not enough conferences and all stuff, because I was moving from California, which was brewing with startups, new conferences, talks everywhere, lot of high hustling energies all over. So that was one of the dragging force for me to not move to Seattle, but I thought like, okay, why not start one? There was like some cool meetups. I think Jeremy hosts Seattle Postgres user group that happens every second Thursday. I don't know the schedule, but you can go to Seattle Postgres user group, CPUG, right? What's the schedule?
Once a month.
Yeah, I think we'll cross-post in our Discord channels, but yeah, long story short, that is the motivation that we had. So yeah, if you are a first timer, we have the website seattlesystems.xyz. We are pretty active on Discord. We have a lot of channels in there. So if you want to be a speaker, we send out the form every now and then, like right before an event. So I have the history of who you want to be, like if you want to be a speaker or not. So I'll definitely reach out. I don't have time yet. I have to reach out to all the past yes responders who have been responding yes to the speakers, but that's the thing. So go to seattlesystems.xyz. You'll find everything on there. The Discord channel is pretty active and stuff. So without further ado, I'll introduce Prateek. So Prateek is a senior software engineer at Figma. And thank you so much, Prateek.
Of course.
And thank you so much, Khwaja, if you are listening, and Momento for sponsoring this event. So Khwaja has been very helpful. I think he never hesitates to sponsor the place and the food, which is pretty cool all the time because finding free places is pretty hard, and this place is not free. So thanks, Khwaja, for sponsoring this event. And over to you, Prateek. So I'll let you speak for your experiences. I think you'll do a better job than me. So, but yeah, thank you everyone again.
All right, can you all hear me? Okay, hey everyone, I'm Prateek. I'm a software engineer at Figma. Thanks a lot for attending this talk. I'm really excited to take Seattle Systems forward. Today I'll be talking about Protosockets. Protosocket is a message communication protocol that was built at Momento. It was actually one of my colleagues who's sitting here, Kenny, his pet project that he extracted out from his pet project and actually productionized it at Momento. Just a little bit of background about myself. I joined DynamoDB in 2018. That was my first gig after doing my master's at Penn State, Go Nittany. And DynamoDB, I worked on the control plane side of things, a little bit on autoscaling, IOPS and capacity management side of things as well. I worked for a couple of years at AWS Marketplace at the data platform team, re-architecting a batch processing system into event-driven system. But I sort of started craving being closer to the metal again than the application. I found a perfect opportunity at Momento for that, where I spent a couple of years working on the SDK team and the server team, doing a bunch of performance optimizations right from the SDK all the way down to the metal. This year, around 6 or 7 months back, I moved to Figma, where I'm working on AI infrastructure for our vibe coding Figma Make platform. For those of you who do not know about Momento, Momento is a caching and PubSub platform. I'm going to give a very high-level architecture of Momento before we talk about the actual protocol that was implemented. It's a very simple two-tier high-level architecture here. As a client, you have an SDK in various languages. You make a request. It goes via the AWS load balancer onto one. The AWS load balancer detects one of the healthy routers and redirects your request to one of them. The router unpacks the request. TLS termination happens inside the router, not at the load balancer because an NLB. Authentication, throttling, and all of that stuff happens on the router. It unpacks the request, sends it to the storage servers. The storage servers persist the request and sends a response all the way back to the client. There's a control plane, which is pretty much the brain of the system. The control plane sends any relevant metadata to the routers about where these storage servers reside, how many partitions there are, where should a client request go to. It provisions the storage servers, it does health check, and like all the state management stuff for the rest of the system. So this is a very high-level architecture of Momento. It's a gRPC. It was traditionally a gRPC-based architecture. So once you connect to one of the routers over TCP, it's an NLB. So it's basically a pass-through. NLB does not really care about what the application protocol is. It just sends the packets to the router. The router is the one that's doing the TLS termination, as I mentioned, and other stuff. And the router to storage communication was over Unary gRPC. and the control plane communication to the router and storage servers are also over Unary gRPC. So just a little bit of the background. This was the architecture circa 2024 June, July-ish, before we started making changes to it. Okay, so I have extracted, the other components. I just have the router and the storage here. That's what we're going to focus on for the next few minutes. As I said, the router communicates over using gRPC Unary to the storage servers. Every Unary request that you make is an RPC. An RPC request has some overhead associated with it. gRPC is basically a flavor over HTTP2. There's a network overhead. Every request has around 100 bytes of network overhead because of the data frames, the HTTP frames. And processing this request, processing every Unary request, either on the router or the storage servers, incurs some computation cost. There are interceptors, there are other invariants that gRPC enforces, like the state machines, error handling. So both of these combined, the network overhead and the CPU cost incurred in processing the request, results in added latencies. So if you're a customer from your client SDK, it surfaces as more latencies. For a server team or for a platform team, it means less throughput from a single box. Horizontal scaling is cool. Throwing more servers at the problem always works, but the philosophy at Momento has always been trying to squeeze out the maximum you can do from one server. That doesn't mean increasing the number of cores or throwing more RAM at a single server, but it means given what you have, how much throughput can you extract from that single server. For a business, again, throwing more hardware is fine. Yeah.
I just wanted to know what kind of traffic were you guys looking at this time?
So the question is?
How much traffic were you seeing? Like how many requests per second were each of these router machines handling?
Okay, now that's a good question. I had one of those slides for results later on, but
okay,
No, that's fine. That's actually a good question. I should mention that. So from a customer perspective, you can throw like millions of RPS at Momento, but every router before we did any of this re-architecture was doing 25,000 operations per second. The workload is 1:1 read-write ratio and less than 1 kilobyte items. So Momento uses RPC perf heavily for benchmarking. RPC perf is a benchmarking tool that was written at Twitter by the caching platform team at Twitter, and it's being used by a bunch of different companies, including Momento right now. So 25,000 operations per second for 1:1 read-write ratio, less than 1 kilobyte items was what these routers and servers together were doing before we changed any of that. Okay, so before re-architecting, the next step was, okay, what can we do? We know we can take, we need a servers to give more throughput. So what's the next step? So before we actually re-architected whole gRPC or any of the protocol, we moved to gRPC streaming, which is like a bidirectional stream. You get a bidirectional stream, and then you send all your HTTP requests or messages over that bidirectional stream. Just to take a step back, in the Unary world, gRPC Unary is over HTTP2, which means that multiple connections can be multiplexed you don't need multiple connections for each request. They're multiplexed over one connection. With gRPC streaming, you can have you get a further optimization where you can send multiple requests over a single HTTP stream. So with Unary, you had multiplexed connections, but you still needed one unique stream for every request. That means opening the stream, processing it, closing it. With gRPC streaming, you can just reuse that stream to send multiple messages over it as well. So reusing the stream, in addition to connection reuse, it's less header, less bytes. You still have those interceptors, but you still get reduced network usage, and you still get reduced CPU cost. For us, that translated to 20 to 30% more throughput, which was good. I was personally happy. Kenny was not. Our founder Khwaja was not at that point. We wanted to do better. What can we do better? Before I go further, one of the downsides of any of these bidirectional streaming libraries or protocols, if you use, is it makes your implementation a little more complex. You get a lot of things for free when you're using an RPC model, a Unary model, like error handling, passing in stuff you want on. passing metadata that you want through headers and whatnot. So the implementation does become a little complex. Okay, so before you can do anything better, you need to know what the problem is. And we were not totally sure what we're trying to optimize at this point once we moved to gRPC streaming. To know what we need to optimize, we need to run benchmarks. One of the benchmarks that really helped us here was flame graphs. So again, using the same RPC perf setup, the load test setup that we had, we ran flame graphs we generated flame graphs on both the routers and the storage servers. And we found a potential bottleneck on the H2 library. So before I go further, this is the stack you're dealing with in an asynchronous Rust ecosystem. So Momento, again, it uses asynchronous Rust. So you have this gRPC layer at the top that's using HTTP2. H2 is asynchronous Rust's HTTP2 library that's on top of TCP. It uses MIO. MIO is like a friendly abstraction over system calls that is provided by glibc. So glibc is basically, you can think of fsync or epoll and open and all the fun system calls that you get from any operating system. MIO is like a friendly wrapper on top of that. And on the bottommost layer, you have the hardware abstraction layer, which is the assembly code, and which provides you an interface to interact with the hardware. So after we ran our benchmarks and we generated a flame graph, there was one particular mutex or a lock that was observed in this H2 library. And every gRPC request that you send, and these things will vary across languages, so this is only applicable for the Rust ecosystem, but every gRPC request you send over H2, every request and response synchronizes on a single mutex within H2. What that means is like, now even if you have like multiple requests over the same stream, all these requests are going to block on that mutex, which is the input and output buffer inside the HTTP2 library. It was pretty hard to spot them. I don't know how Kenny did that. He had like a lens in his extra lens that he was able to spot a particular stack frame in the flame graph that's called lock contended. So if you ever see like a bunch of lock contended stack frames on your frame graph, it means there is a potential problem. What does that mean? Like, sure, we saw these flame graphs, and we found these stack frames that says lock contended. What does that actually mean? Within Momento servers, what we noticed that each runtime thread parks itself for hundreds of microseconds and is not able to make progress when it hits this particular condition. So a router might have 6 to 8 runtime threads that's processing a bunch of different requests. Whenever it had to synchronize in this particular buffer, one of the threads made progress, but 6 of those threads potentially spent hundreds of microseconds waiting, just parked in the kernel, waiting to be woken up before it can process that request further. There's this issue still open. I think I actually Googled it this morning, and this is still open on S2 side. The title kind of gives it away. Library does not scale with multiple cores. So it basically means that if you keep increasing the number of cores or double the CPU, it's not going to help. That's the maximum you can do with the H2 library at least. So then comes Protosocket. Protosocket, as I said, was one of Kenny's pet projects that he pulled out from his pet project and threw it into the Momento ecosystem to see how it behaves. It's a message-oriented. It's not RPC-oriented. It's message-oriented. It's just over raw TCP. It doesn't have too many opinions. If you want ordering, you can use it in a way that enforces ordering. If you do not, then you can use it as is. It doesn't have any shared state connection. So what that means is like every connection you make now from your router to your storage servers, there is no shared synchronization between the connections, which was the case in H2, where even multiple threads and multiple connections were contending on a shared state or a shared buffer. In case of Protosockets, every connection gets its own input and output buffers, and even within those buffers, the synchronization points are quite minimal. I won't go into super nitty-gritty details, but if you look at it's an open source library. There's a bunch of cool stuff going on between swapping hash maps to avoid, to keep these locking points as minimal as possible. Okay, so we spoke about this stack. Now what do we get? So these are the two abstraction layers that we got rid of. Once we switched from gRPC to Protosockets between the router and the storage, we got rid of gRPC, we got rid of H2, the H2 layer. We're directly using TCP. We still use MIO because it gives you those friendly abstractions over ePOL. It's a readiness-driven library. It's like the philosophy of MIO is readiness-driven events. So you don't have to reinvent the wheel. We still use MIO and directly talks to the operating system. We use Prost. We still use protocol buffers. Prost is a library that in the Rust ecosystem that's used for protobuf for encoding and decoding messages. Protocol buffer was still a valid choice. It compacts your data. It packs your data more compactly as compared to JSON or even message pack, as a matter of fact. So we still went ahead with that. Okay, so I spoke a little about this before. Prior to any of this re-architecture, our routers, or one router, one storage server with a replica, combined was doing 25,000 operations per second with P39s less than 5 milliseconds. So that's kind of a benchmark Momento tries to test against. It keeps changing. But with Protosocket, they were able to do 70,000 operations with P39s less than 5 milliseconds, which is almost like a 3x boost. So if you needed 100 servers for your workloads, now you need like 35, 40 servers for your workload, which directly impacts your company's revenue margins, and not revenue, but margins at least. We also noticed that the degradation, like even if you're pushing your workload beyond 70,000 operations, the degradation in latencies was quite minimal compared to using Unity gRPC. So in Unity gRPC, at like 30,000, it went from like 5 to 40 milliseconds. But with Protosockets, if you went to 80,000, it goes from like 5 to 10 milliseconds. So the step-ups in the latencies as you increase load was also seen to be more graceful in case of Protosockets versus gRPC. This is actually pretty cool. This happened after I left, like 6 months back. I was like so impressed that the team did it, and I wanted to add this. Earlier, we were talking about just the communication between the router and the storage servers. One of the goals was to extend that to the SDK, which comes with its own set of challenges. Within your VPC, within your own ecosystem, within your own servers, you can do a lot of things, right? Like there's no authentication issues, there's no security concerns. But once you expose this to the client, you kind of open a different kind of worms. So the current architecture, from the first slide or the second slide to now, this is how the current architecture looks like. You have a client SDK in multiple languages. I think this is in a couple of languages implemented already. So the first thing you do is you talk to the control plane via the NLB. I'm missing an arrow here, to discover all the routes, like all the routers. So the first thing the client does is it establishes a connection with Momento. It gets all the available routers, the IP addresses of all the routers. As a part of that first request, authentication also happens. Once it gets all the addresses in a round-robin fashion, it sends the request to the routers over this long-lived bidirectional Protosocket connection. As an additional mechanism, the first message that you send over this Protosocket connection is an authorization or authentication command. So the first step of authentication is when you get the addresses by talking to the control plane, and the second step of authentication plus authorization is the first message that you send as a part of this long-lived connection. If you try to send something else, the routers are going to reject that message back to you. And this, so router to storage was happening over Protosocket, and the SDKs to routers are also now happening over Protosockets.
Learn about the token.
How does the router learn about the?
The client SDK, I'm assuming, comes to NLB and the control plane.
Yes.
The control plane communicate back to the routers about this token, or like you said, the clients directly talk to the routers after that, and they do some authentication. So this is one thing.
It's just the authorization. Yeah. So it does send the token as a part of. Correct me if I'm wrong, Kenny, because I was not involved in this.
So the initial discovery of the routers
happens via just plain HTTP JSON. That is an authenticated and authorized call. That lets us do things like give customer-specific routers or things like that. But then the direct connections from the client SDK to the routers, those are separate connections, so those also need to be authenticated and authorized. So you pass your auth token into those connections as well.
It's a JWT, it's a JWT token that's passed to both of them.
Just one more question. NLB already supports TCP, load balancing over TCP, right? And you're over TCP, so why not just go through NLB again?
You want to take that?
Mike,
Oh, sure.
should repeat the question as well.
Yeah.
I think your question was, NLB already does TCP load balancing. Why not just connect to your routers through NLB? And that does work. We've done that. But why not is because NLB charges you an extra 1 to 200 microseconds, and it also charges you dollars and cents for pushing data through it. So it's it's more expensive and it's slower. And so if you're optimizing for steady state requests to be as fast and as inexpensive as possible, it's nice to bypass NLB when you can. Also, if you're doing like a VPC peering relationship with a client, you can do VPC local routing and have basically free networking, client to server, which is pretty cool.
Do you peer with your clients? Do you peer with your clients? And what are the limits there?
We've investigated a couple of different ways to peer. Usually we do the private link endpoints, but this new pattern was made in part to help ease the way that we would vend out like 10 dot IPs. This is very new stuff, like Pratik is saying, and this is unblocking us to be able to give nice VPC peered CIDR routes to some of our interesting customers.
How does L-checks DNS reconciliation happen? So let's say one of the routers go down, how does the client library know about the new nodes it needs to connect? How does it reconcile?
It refreshes the addresses. It periodically refreshes the addresses back to the control plane, yes. So the question was, how does the client know if there's a deployment on the router or something went down and a new router came up? The SDK keeps refreshing the list of addresses from the control plane.
Just one follow-up question. Typically, even internal to your internal infrastructure, these components are pretty close to the storage layer, so they generally don't, like a router does not have like authentication, authorization, or like maybe a DDoS attack prevention or anything like that, usually, right? So would you add those directly in the path, or would the router have that functionality?
Would the router have DDoS, authentication, authorization, things like that? Yeah, Momento's router is a multi-protocol web-facing front end. So it does a lot more than just client SDK Protosocket stuff. It also has HTTP support. You can put like a URL into an IMG tag on your website, and it will load values out of your cache like directly into a DOM. So there's a lot of extra stuff that you can do here, and like fine-grained access control, like a per key scoped tokens that you might imagine are important. If you're giving someone access to to your cache through their smartphone's browser. We've also got like topics, which some of our customers use for like chat or for video game state propagation out to end users. So that router box, it's a lot more than just like an internal service detail. It's kind of a core to the way that users interact with Momento.
And the router is also Rust.
Yeah, yeah.
Thank you.
Yeah, and of course latencies. With NLP bypass, these are like some of the latencies gains that the team witnessed. Like at P50, P99, P39s, it's pretty much double with NLP and without NLP. There's obviously a bunch of trade-offs when you're doing some of these things outside of your traditional infrastructure ecosystem. Proxies, firewalls, they all understand HTTP. You just can't get away with it. As I mentioned before, implementation is definitely more complex. There's a lot of things you get with HTTP for free. Yeah.
Let's go back to the previous slide. I just had a quick question.
Sure.
The one before that. So you already have routers. You said routers do a lot more. Just curious, you could have also published the storage IP addresses at this point in time.
The question is, why do we need the routers if we have Protosocket and just not publish the storage IP addresses at that point in time?
You have to make clients back?
Yeah, you need to make clients fat, and then placement is at issue here. So the control plane does a lot of stuff behind the scenes. If you're trying to scale up, scale in, or do a deployment and change like your cache topology, there's a lot of coordination that you've got to do between the control plane and any of the clients. So inside of AWS, when you're sending your state, like the state of your storage updates to your routers, that happens very, very quickly. If you're doing it over a possibly public network to the client SDK, you may see elevated errors. Our customers reach out to us when we return them one error in a lot of cases. And so our deployments have to depend on things like HTTP2 go away. Traditionally in Protosocket, we've done some stuff there, but I expect that we'll hear from customers as they start using the Protosocket version that they don't like that they see a moment of errors on a deployment. They need a graceful failover. So yeah, basically to make sure that we don't give users errors, we don't publish those storage IPs directly. Also, they don't have authentication authorization built into them right now. It is a thing that we talk about though on a regular basis. Like, is this customer or is this use case the right time to add our authentication and authorization to our storage nodes and publish them? It's something that comes up, and I wouldn't say that we're fully settled on the request flow that we have, but yeah, for now the router is the thing that we talk to at least over the public network.
The curious thing was the next slide, which talked about 330 microseconds at P50. So I was wondering how much would be 300 seconds. So how much of the 300 microseconds will you shave off if you go to the storage directly? This is 2 hops, right? 300 micro 2 hops?
Yeah, that's 2 hops. This is I think these were client-side latencies as well. I don't remember the test setup for this test. I'm pretty sure this was a client-side test. I didn't run these tests, but yeah, and I had it in the back of my head that it was about a 200 microsecond difference for NLP bypass. These are with, I think, larger nodes pushed at much higher throughputs. We've got 4x or 8XLs that we do 600,000 or 700,000 requests per second on now, which is quite hot. And I think that's what these tests came from. As for how many microseconds the router is charging you, that is in the low 100 to 150 microseconds territory when you're using a non-blocking RPC library like Protosocket. When you're using gRPC, it's much more variable due to the contention, the lock contention inside of the H2 library.
And this is placement inside the placement group, I'm assuming?
This is not using placement groups, no.
Wow. So, wait, that's not what I heard. By the way, I thought the P50 was with placement groups. Because
Was the P50 with placement groups? So you may have heard so there were like 7 or 8 different permutations of this test that were done. You're you're like poking at something that I watched happen on the side.
I'm waiting for my Yeti month, that's all. Watch out was me.
Oh yeah.
Yeah, this was directly copied from one of the Khwaja's posts. You should probably ping him and ask him as well.
Oh, okay.
All right. Any more questions on this architecture before I go further? Yeah.
A couple more questions on so at what point does Protosocket make sense? Like I understand that if you have like sub-millisecond latencies, this actually has a lot of difference. But if you're running like a storage service where, let's say like a database or something, where your latencies are more on the orders of tens of milliseconds or something, would this optimization matter? But the other difference there is also we are sending more data back if you are doing like analytics. So I'm curious about how this performance changes as you scale up the data, the payload, and also, yeah.
So if I understand the question correctly, you're saying where does this performance improvement actually matter?
Yeah, like if you have a database that's doing
Yeah.
analytical queries and returning, let's say, let's say hundreds of kilobytes of data.
Right. In my personal experience, I've seen it matters when your tail latencies are impacted. So you probably wouldn't see it at P50, P90, P99, but you'll start seeing them at 4 nines or 5 nines. For product teams, usually I've also seen they make so especially if you have a microservice-based architecture, you don't know how many layers you're going down, and every millisecond that starts to add up pretty quickly. And that's just based on my experience in the past, where even a millisecond of tail latencies start like mattering when there's a cascading failure situation, when you have a retry storm, in basically a SEV situation. In steady state, you're probably right. Yeah, no one cares. But once any failure mode hits, it's like a metastable failure at that point. So I think at Momento, that's why I think folks are quite performance focused, because we are tail latency focused a lot.
When you're talking about tail latency, like you've got, I mean, you also earlier talked about like people loading this stuff from like the browser on their phone. I mean, like that's gonna have tail latencies if you're coming from somebody's browser on their phone. So like you must be talking about like assuming that like just clients maybe inside the same region of the same cloud provider where you're running the cache. Is that kind of the focus here?
So what's the focus of the tail latencies? Yeah, from the user's perspective, sure. Like if you're loading from the phone, you're not going to expect to see loading an image in 300 microseconds. But if the server can't generate the response for you in less than 5 milliseconds, then the user certainly can't receive the response in less than 5 milliseconds, right? Like the performance of your server limits the best performance that a client could possibly see in theory. So Momento, yes, is available to users over a public link, but Momento also has a lot of traffic that stays local to AWS and local even to availability zones, and in some deployments they're AZ aligned. So it's kind of one of these things where if you're fast enough for your in AZ customers, you're going to be fast enough for your browsers. So I don't like it when people try to measure the latency to a smartphone when it's going over some public Wi-Fi at a coffee shop or whatever, and they're like, hey, why is this taking 60 milliseconds to load? It's like, well, take it up with Starbucks.
Also, I think real world applications are not going to make one call, like especially somebody on the browser, like Amazon web page, it's going to be like at least 20, 30 calls before either user gets results. So every millisecond starts adding up quite quickly.
One slow request slows down the entire page load at that point. I think that's one of the reasons Dynamo was built initially, wasn't it? Okay. So that was the talk. I just wanted to highlight a little bit of my personal experience with async Rust. I started on control plane on DynamoDB, which was not very systems programming heavy. We still use still JVM, a lot of fleet management challenges, not necessarily systems programming challenges. spent some years again on like the application side, using a bunch of AWS tools or toys that I called to build like a distributed system on top of it. And after that, I sort of moved to Momento, which was like my systems experience. So I sort of moved like top down. And if I were to like go back 7 years, I would have like moved bottom up, where I still don't care about this stack, like the hardware level and what's happening inside the machine, but I would definitely start here. If you're like new to system programming, which probably most of you are not, but still if you are, I would start like bottom up. Open an OS book, write your own HTTP server, simple HTTP server, try to optimize it, make it event driven by using like event epoll and other primitives, then go to the higher level abstractions and finally to the application. So just wanted to share like my personal experience, because initially I had a very difficult time understanding any of this. Just acknowledgement to Kenny, you've heard from him already, and Khwaja just for sponsoring this and being like a great champion, across the past 10 years. Yeah, that's it from me. Yeah.
So this is all written in Rust.
Yeah.
You guys have like, I just looked, you guys have a really impressive list of languages that you support. How are you integrating, out of curiosity, those the languages to the Rust implementation?
So it's gRPC. So before any of the Protosocket, so Protosocket is only in one of the client SDKs right now.
Okay.
But before Rust, I think we're implementing that in Golang using foreign FFIs. So I think the model there would be to use FFIs to integrate. But before that, it's like all gRPC.
Okay, so all of those clients, with the exception of the Rust one, are all still using gRPC, the
Yeah.
router?
Yeah,
Okay.
yeah. But as I said, this was like built like in the last 3 months, like the client side layer. The server was like built
And
last
the
year.
router stuff's all Rust all the way through?
Yes, the router, storage server, even the control plane is in Rust. It was in Kotlin, but even that's rewritten into Rust now. So it's, you're surprised. All right. Any more questions before I?
Rust. What other justification? Sorry? You like Rust? What other justification?
No, I think so. We were initially a Kotlin shop for the most part. Moving to a systems first language like Rust gave a lot of performance benefits on the server side, which is like the routers and the storage servers we spoke about. And then just having control plane like in another language, it just makes like the onboarding for learning curve, and like it's a mono repo, so the consistency of different things, it just makes it easier over time. And we had to rewrite a control plane anyway, so why not rewrite in Rust, which like half the team already knows and half the system's already written in. So.
Makes sense.
Cool, that's it from me. I'll give the mic over to Somu now. Thank you.
That was a good job. I would find it.
Thank you. Oh, I have to use this.
Good. Hi, my name is Somu. I'm from Amazon. I work in Bedrock now. Until a year ago, I was in Dynamo, building a bunch of replication services, specifically regional and global. In this talk, I was asked to give this talk like 2-3 weeks ago, and I've been lazing around preparing for this talk. But I thought, okay, I'll talk to you guys about how we build global tables and what is the thought process which went into us building global tables, and give you a small demo of how things work and what is under the hood for global tables. If any of this content is like familiar, just let me know. We can skip over the slides because it's already like 7 o'clock and I don't want you guys to stay long, so we can kind of skip some of the slides. A quick primer about Dynamo. Dynamo was built as a highly scalable and highly available key value store. To scale Dynamo's tables horizontally, we just kind of partition the data across multiple storage nodes. To make it very highly available, we kind of split data across 3 availability zones. And now we have to replicate data across 3 availability zones for the same table. We use a version of multi-pack source, and this allows us, what this does is selects a leader in one of the availability zones. So when you make an update item call, it goes to the request router. Request router does the admission control, authorization, authentication, and then looks up, hey, where does this key belong? And then picks that particular storage node where, picks one of the 3 copies actually of one of the 3 storage nodes to say, hey, can you access this data? And if that storage node is not the leader, it's going to point you to the right storage node in the right availability zone to go write that data. The leader receives this request, generates a log entry. The log entry is replicated across the other 2 storage nodes. Once 2 out of the 3 say, yes, this is durably committed log, we acknowledge to the customer saying it's successfully stored. Now, this is like the high-level view of how things work, and a single update item works in DynamoDB and regional DynamoDB. And the reason we build it to be highly available is to endure failures such as single AZ going down or node failures, so that we have very high availability in terms of what we're building for a key value store. And being able to shard across multiple storage nodes gives us the scalability which customers will look for in terms of like how much data you can store, and without losing the performance. And that was a key thing which we were always looking for. Because as data size grows, you can see some of the databases actually slowing down. And in Dynamo, we didn't want to kind of do that. We wanted to kind of build a system which scales for storage, but you don't lose the performance as you kind of scale for storage. So a couple of key tenets in Dynamo is like having predictable performance and having seamless scale. I think these were 2 things which we always ingrain in Dynamo. Is like these are two of the most important things we build into every feature. And Dynamo supports 2 consistency modes for reads. One is eventual consistency, and the other is strong consistency. Eventual consistency basically says that, hey, you can read a copy of not all your replicas will converge to this, to your write immediately. Some may take some time to converge. So if you read from those replicas, you could land up getting a staler version or older version of your data, right? This is super critical. This is super critical for some applications which are really which really don't require strong consistency. For example, if you're watching on ESPN the score of a game, you really don't need strong consistency. You don't need to kind of have this score immediately as soon as it's updated. You could live with the score which is 5 minutes old or a minute old, unless you're a diehard football fan. So in Dynamo, when you make an eventual consistent read, the request router routes the request to one of the 3 replicas. It doesn't care. It just says, hey, I'm going to route it to one of the replicas. Just give me what the data is, right? Because it doesn't care if the data is actually converged to the latest write or not. The replicas converge to the storage node has the latest write or not. So the other mode Dynamo supports is the strong consistency, strongly consistent reads. And strongly consistent reads are for applications which really need the latest version of the item to make any progress. For example, control planes. If you're making any changes to control planes, or you kind of depend on your control plane would depend on the latest version, state of some resource in your system, then you need a strongly consistent read. So Dynamo supports strongly consistent reads as well. And how do we implement strongly consistent reads? Strongly consistent reads go always to the leader, because we know if the leader has accepted write and we've acknowledged it, you're always going to get the latest write from the leader. So strongly consistent reads go to the leader.
Can I ask a quick clarifying question? Is that the leader going to be like that availability zone for all the keys, or is it like on a key by key basis? Like this key might have a leader here, and that key may have a leader in a different.
Good question. I think leaders can be anywhere across any availability zone. And Dynamo shards a table into continuous key ranges. So for a bunch of keys, which that particular storage node hosts, it would be the leader.
Okay, so it's not one key per, but it
No.
is smaller than the entire availability.
Yes.
Got it. Thank you.
If anybody wants to read a lot more about the consistency models, I would ask you to kind of take a look at Doug's paper, where he talks about data consistency through baseball. If you're a diehard Indian fan, then Akshat has written one with cricket, using cricket as an example. But definitely, Doug's paper is super interesting, and him using baseball kind of tells you different kind of consistency modes which databases can expose and where they are very useful, right? As application developers, we always think that strongly consistent is the only way to build systems. If Khwaja were here, he would tell you that eventual consistency is good enough in Dynamo. And the reason is that in most cases, Dynamo's replication is so fast because 2 out of the 3 storage nodes have to tell S before it can commit data. So 66% of the time, your eventual consistent reads would land up being strongly consistent no matter what. And the replication is so fast that the third replica would also have the latest data by the time you make a round trip and come back to Dynamo, right? Now, given the fact that Dynamo is built across multiple availability zones, withstand availability zone failures, we still had customers asking us about multi-region setups. They wanted to go build multi-region data. They wanted data stores in multi-region because they had a lot more stringent requirements on availability and continuity of the business operations, right? Because no system is immune to failures, 100% failures. You can have hardware failures, you can have software failures, you can have a deployment go wrong, or you can have something else go wrong, and then so yeah, if one of the region experiences problems, then you definitely want to shift your traffic away to another region and kind of be able to continue your business operations, right? But this continuity of operations has 2 key elements. One is recovery point objective, and the second is recovery time objective. Recovery time objective is slightly easy to kind of think about. It is how soon do you kind of recover from your failure, right? It's a mean time to recovery, mean time to repair, right? You can call it with other names. So this kind of defines how long you're going to be down and how quickly you're back up and running. The first one is the recovery point objective is what kind of tells you how much data can you afford to not have when you fail over to the new region, right? Do you need all the data? Do you need the last write which was acknowledged in the region, or can you lose data which was like 5 minutes worth of data? Different applications have different requirements, and that defines what continuity of your business applications is going to be. There may be some customers who say, "Okay, I can lose 1 day worth of data." There may be some customers who can't lose even one single write. And at the same time, when a lot of the application developers are kind of thinking about multi-region setups, there are 2 things which go hand in hand. One is the cost versus resiliency, right? I store backups all the time, but I never restore from backups. Backups are a very cheap way to kind of have disaster recovery as a disaster recovery option. And backups also allow you to kind of recover, but it takes a long time to kind of recover from a snapshot. Like I had a friend who was telling me that the 16 terabyte restore was taking like 5-6 hours before his business could come back online. So backups are good, cheap, but the recovery time objective is going to be really, really high. Likewise, you could have something where you have a warm replica, which you kind of do not use at all, and write data to it from time and again. It's going to be low cost because you're not doing the reads. You're just kind of keeping regular snapshots and keeping it up and running, but you're not using it at any point in time. Or you can have an entire sort of a warm standby, like a DynamoDB global table with a multi-region replica where the other replica can do all the reads and writes which the other replicas in other regions do. So Dynamo's, to give a little bit of history, Dynamo, when we kind of started implementing global tables, firstly, global tables is the work of a whole huge big team, just not my work. This team of smart engineers, the team of smart engineers like Kenny and Akshat who set up the groundwork as well. Kenny set up a bunch of the groundwork for global tables by implementing logs and CDC for Dynamo back in the day. Then Akshat and I worked on a bunch of global table stuff together as well. So when we started implementing, one of the key things we were asking was, what are customers using this for? Customers are using this for disaster recovery. They wanted high availability, and they wanted the same performance as regional DynamoDB, right? So the first one we implemented was asynchronous global tables. We also saw customers implementing this by themselves using libraries, and it's really hard to implement this. I'll go into details why it's hard to implement using a library. But we did, as soon as Kenny, we all implemented update streams, the first things customers did were like, hey, we're going to use this to kind of build replication, cross-region replication. And it's very hard to get that protocol right. So everything in Dynamo depends on the replication log the leader generates. Leader of partition generates and replicates regionally, right? The log is the database for us, and this is what even Peter was referring to about a couple of years ago in reInvent. The log powers backup restore today. It powers update streams. Update streams powers Lambda triggers, which I use frequently, but I don't know how many of you use it very frequently, but update streams also powers Lambda triggers. It powers asynchronous global tables. How does it power asynchronous global tables? We have a small replication engine, which sits outside Dynamo, actually, and takes all the change data capture and replicates it to another region. On the outside of it, it looks like a very easy problem to solve, and we did think it was a very easy problem, and we can solve it outside Dynamo. But one, it gets very complex quickly, and two, it gets very inefficient quickly as well, because you have to solve the problem of, there are two problems you have to solve. One is replication, and one is how do you deal with write conflicts, right? Today's async global tables also does not have any limits on how many replicas you can have. You can have n number of replicas, n number of regions in a asynchronous global table. And the replication engine for each region pair is individual. We built it this way because we, again, want every pair of regions to have their own high availability. Want it to be highly available. So every pair of region gets its own replication engine. So even if one replication engine has stalls because a region does not take any writes, the other replication engines can keep chugging along. They don't have to worry about one region being down or one table not being able to take updates. So this diagram goes over a timeline from left to right. There are 5 regions in this particular slide. Write happens in region R1. Once the write is successfully said yes to the customer, the write is replicated asynchronously to the other regions. The only guarantee is the write will get replicated. There's no guarantee that they will get replicated at the same time. So each region can land up seeing the write at any given point in time. Right? Now, on top of that, the replication is bidirectional, right? And the replication is bidirectional across all regions. So if you have a 3-region pair, then you have like 6 ways of replications going around. Strongly consistent reads are strongly consistent only in that region. So if a region has accepted a write, you can definitely see the writes in that region. The other regions, if you perform a strongly consistent read after writing in region 1, the chances are you may see or you may not see the latest write which happened in region 1, right? But you will land up seeing that write at some point in time, eventually, right? And that's why this is asynchronously synchronized regions. If there are 2 writes happening to the same key, then we have to solve the problem of write conflicts. Which write should persist over the other write? Like, because 2 regions don't know the writes are happening to the same item. So how do we decide to resolve this conflict? We first tried it externally by saying, hey, we will store timestamp with every item, right? Every item is timestamped and has its own region. When we built the library, we kind of took the same idea. So we stamp every write which comes into Dynamo for a global table with some metadata which says at what time did this write happen and what region wrote what region is this write originating from. Now, if there are 2 writes which happen at the same, 2 writes happen to the same key, we will use this metadata to resolve conflicts. We will first use the timestamp to see which write happened before which one. The timestamp is a glorified version. Like, let's say I write to region 1 before region 2. Region 2 could land up getting a smaller timestamp, so region 2's write may get clobbered. But it's just a way of like us saying, okay, this is how we're going to do conflict resolution.
How accurate is your time? How easy it is?
We use time sync, which is fairly at P90. The drift is very small across regions as well, right? Have we seen time drift like upwards of 3 seconds? Yes, we do see sometimes, like P100 of 3 seconds. The thing is that one of the writes is going to get clobbered either way around. So it's not much of a difference which one gets clobbered at that point in time. Right, so asynchronous global tables resolves the write-write conflict with last writer wins. This is one of the key things which is super important to remember about this, that if you're writing to multiple items, if you're writing the same item and from multiple regions, only one write is going to win over the other writes. Right?
I have a question. Can a single client talk to multiple regions within the same session? Does it happen, or does a single client always talk to the same region?
You will have to spin up 2 different DynamoDB clients for 2 different regions. You can't talk through the same client. Right? And I don't think, yeah. Now, this has very interesting properties. One is if there is a region which is not reachable, or there's a region with a failure, replication to the other regions will continue. Once a region recovers, then replication will catch up to that region. If for some reason that the region doesn't come up within 24 hours, then if the replica is down for 24 hours, usually we kind of land up disassociating the replica. This does happen if customers use their own keys to manage the encryption, and sometimes they will yank the keys. So Dynamo can't replicate, in which case we'll say, okay, fine, after 24 hours, we're just going to not replicate anymore, and we're going to disassociate the replica. And also there was a streams limitation back in the day, which was like streams only are persisted for 24 hours. After that, we start losing streams. If a particular region is isolated, it's the same thing again. The other regions are available. And the region which is isolated is also available for reads and writes. It just doesn't get updates, right? It's very eventually consistent at that point in time for writes in the regions the other regions which are happening, right? So your applications would not notice there's a network partition or the region is isolated. The applications would continue to kind of work on the respective regions, just that they won't see the writes. They would see the writes after the network partition is recovered. So once we built this and we kind of had global tables going, it was kind of interesting to see how quickly a lot of customers adopted global tables and how quickly there was a lot of impact on like just disaster recovery as being the scenario. And a lot of other customers wanted local reads, which were really, really fast. And that became another application as well, where customers were looking at reads which they wanted to perform in region and was quite fast. And they didn't mind reads which were stale. But there were a lot of other customers who were like, hey, your neighbors north provide strong, consistent reads. You can read your writes from anywhere. We want to kind of have a global database or global data store which would do this stuff for us. They went ahead and built stuff around DynamoDB global tables. They would write to a single region and read from that region, which supports strongly consistent, but they had to kind of keep track of which region this is. This worked for some customers, or some customers even went and did quorum reads, which is like, hey, I will replicate the data like in 5 different regions and then do quorum reads and then read the data and do my own conflict resolution. But all this didn't sound like it sounded like a differentiated heavyweight lifting, which their application did not need to do. Right? We knew that we can go and implement something which they can make use of for reading their own writes. And also, none of this provided a zero recovery point objective for them. If a region failed or a table failed, then the recovery point objective would be like they would lose as much data which was not replicated. Right? So we said we'll go build something which will kind of do strongly consistent global tables. So we call this as multi-region strongly consistent global tables. It's a whole mouthful to say, so I'm going to call it Mercy, which makes it easier for me to kind of say throughout this talk. But the first thing we wanted to solve is we saw log serialization across availability zones. We wanted to solve how do we build service which can serialize logs for us across regions. I know Mark gave a talk here a couple of months ago. I don't know when Mark gave a talk. So both DSQL was also in the oven, and Dynamo was trying to do strongly consistent global tables, and we built something called as we kind of said we should build something called as a multi-region journal. So both of them use multi-region journal as a log mechanism to kind of replicate logs across regions. Multi-region journal spans 3 regions today, the 3 regions in which you have your replicas. All it does is it kind of lets you append logs across 3 regions. And it would only kind of append a log and return a success if it can do it across 2 out of the 3 regions, and then give you a callback saying, okay, the log is appended. Now, you can also have listeners in other regions. You will also need to have listeners from these regions because the logs can be appended by any writer. So you want to listen to all the logs which are appended so that you get all the logs in the serial in the same order as they get appended to multi-region journal. So multi-region journal was built to kind of solve a bunch of the problems which we want to solve in terms of like, hey, how do we not lose, how do we kind of do log serialization across multiple regions? The listeners need to listen because they need to get all the logs in the order in which they're appended, because append can happen from any writer. So if you want to kind of keep track of how do you kind of append how do you make sure that you don't miss any of the logs, then you need to have your listeners listening to this multi-region journal. And the multi-region journal would give the call back to the listeners in the same order the logs were appended, right? And it would give you the log entry. Now, Mercy Global Tables uses multi-region strongly consistent global MRJ to build upon. When a write comes into a single region, first a log is returned to the multi-region journal. And once the listeners get the call back saying, hey, there is a write for this particular item, they would go ahead and apply it locally in the region. This is as simple as that. Now, when you perform a strongly consistent read in the region where the write was done, this is very trivial. You can always read your writes in the region, right? This is not hard. When I perform a consistent read in a region which has not got the write, how do I know I have the latest write, right? There's no way that region can know it has the latest write unless it knows that it has read everything in the log up to that point in time, right? So the consistent read actually generates a heartbeat to the multi-region journal. Think of it as a read barrier, right? It's going to send a read barrier or a tracer bullet to the multi-region journal saying, hey, I need to know, just write this heartbeat to the record, append to the journal, and then give me a call back. Give me all writes I've missed so far. So once the heartbeat goes in, the listeners will get the call back for the heartbeat, but they have to kind of, to go get to the call back to the heartbeat, they have to catch up to all the writes they've not kind of applied yet. So they start applying all the writes they've not listened to it. And then when the heartbeat appears, you can kind of read whatever item is applied and return back. So this is how strongly consistent reads work on multi-region journals, multi-region global tables. Now, if you have writes happening to the same item in 2 different regions, the writes would be applied in the order the multi-region journal serializes them to the log. So if there's a write B in region R2 and a write A in region R1, they both would try to append it to the multi-region journal. Write B gets appended before write A. The listeners in all the regions would listen to the write B log. They would write the first update to the item, and then they would apply the second update, which is the write A. This is the strongly consistent read in the region in which you do the write. Also heartbeats today, and we did kind of take this route. It does add a lot more latency for strongly consistent reads because the heartbeat is an expensive operation on the multi-region journal. The write is very expensive, but with depends on the region set. Like if it's IID and CMH and PDX and you're doing a write and doing a strongly consistent read in IID, it's about like 20 to 30 milliseconds round trip because the heartbeat has to be serialized and then read back. And usually you're caught up to the writes up to that point in time. So it's just a matter of just listening to the heartbeat back again.
The heartbeat is based on a timestamp or what's the?
It's just a heartbeat. We did not take any timestamp into account for that. So you just heartbeat and you just return back the heartbeat. You'll have an identifier with the heartbeat. Yeah, you have an identifier with the heartbeat. You're right, like because there may be multiple strongly consistent reads you're performing, so you want to know which one is your heartbeat. So you do have the item key which you're trying to read and an identifier which says, okay, this is your heartbeat. So The read became a write, yes. Not my favorite option.
I imagine you probably group strongly consistent reads that come very close to the same time together into a single part read, right? Since it's so expensive. If you have 100 consistent reads that arrive within 100 microseconds of each other, you could write just once and give the same read barrier to all of them. Yeah.
Yes, you could land up doing that. You could kind of have a whole read barrier for a whole set of reads. But usually Dynamo reads are across all over the partition. So if it's within the same partition, you kind of try to deal with it, yes, you can land up doing that. But if it's across other partitions, every other partition would do its own heartbeat to the multi-region journal so that you can get the writes.
The partitions are same across all regions?
No, good question. The partitions are not same.
Could you not do a hash value of the first version? When you write the second version, you send the hash value of what the previous version is. So when the write occurs, you'll be certain that you're not overwriting a version that is a mismatch. So at least you'll know if there is a conflict of writes in one sequence.
Very good question. I think if I'm writing from the same region, yes, I know that that conflict won't happen. But if I'm writing from different regions, so this was something we were going through. DSQL does this slightly different than Dynamo. Dynamo allows you to write from all the regions. So partly because Dynamo applications, usually customers land up sharding keys across different regions, and there's very few applications which write to the same key from 3 different regions. So we did optimize for saying that, hey, you can write from multiple regions simultaneously, even if it's the same key. And I'll get to that slide in a few seconds where I talk about how we actually kind of use a different technique to kind of make sure that the applies are idempotent. So asynchronous replication had the replication engine outside Dynamo, reading streams and doing a bunch of work. Multi-region strongly consistent DynamoDB tables use the replication which is inside Dynamo now. We just kind of moved the replication piece inside because it had to happen before we can reply to the customers. So write comes to the request router. There's a global table shard processor which is basically responsible for a set of keys for a given table. It reads the latest version of the item from the DynamoDB table, generates a log entry, appends it to the multi-region journal, and the multi-region journal gives a callback to all 3 regions saying, hey, I've applied this new update for this item. The GT shard processor then tries to write it to the DynamoDB database. If it's successful, then it would return back a success to the customer. If it is not, then it would return an error to the customer. And this can happen because the thing we went for was like deterministic execution. What we said was that if all 3 replicas started with the same state and had the same set of commands to apply, they should all converge, right? Because the order in which the commands come in are the same. But the commands have to be idempotent and have to be deterministic in terms of execution. So every update we do to a DynamoDB item is converted to a deterministic execution. And how do we do that? We take the current value of the item. Let's say I'm trying to increment a counter. We take the current value of the item, generate the new item, and then say, hey, write this item if it matches the previous version of the item. So this is a log entry we generate, which says, hey, here's the command you need to execute. What this allows us to do is that if 2 different regions are trying to write to the same item and they're reading the same value of the item from the database, they'll end up one of them lands up succeeding, the other one lands up failing because they're deterministic execution. Now,
the one that fails is the one that comes second. The timestamp of the second one was.
Yes. The one that fails is the one which gets appended to the log entry the second. So it does fail. And this was one of the things we introduced. We had a lot of debate about introducing this exception because what Dynamo goes for is like, hey, if you had an application which was working for a regional table, it should work for a global table as well. But just introducing this application meant that customers had to handle this exception and retry the update again. A big difference in Mercy global tables is latencies. This is a killer. I will kind of give you a demo on how latencies differ between both async and Mercy global tables. But the latencies depend upon the 3 regions it's a PEC. For example, IID to PDX, IID to CMH, UC is 20, UC is 2, the latency is round trip is 25 milliseconds, so it's usually okay. But if you have a write which is happening in PDX,
that's going to take a longer time. And likewise the read as well, because like Akshat mentioned, the read gets converted to a write. So all regions are not equivalent. If a single region has issues, then that particular region can't take reads or writes, but the other two regions can take reads and writes. We are fine. There's no issues with that. If the single region is isolated, the single region won't be able to serve strongly consistent reads or writes. It will be able to serve eventually consistent reads. It's still fine. The other two regions will still work fine because the multi-region journal is its mechanism for replication of data.
One question. Do I know that if I requested a strongly consistent read, I actually got, wouldn't that be a 500? I thought that should be like a 500.
For which one?
The last part that you said, that if those two fail, and if I request something from...
Oh, this is the network failing between these two.
Yeah. And if I request something from US East 1, and I say I want a strongly consistent read, would it give me like 500, or would it actually give me an eventually, like,
It'll give you a strongly consistent read, because if it can heartbeat to the multi-region journal, then it's caught up to all the writes. So it's going to heartbeat.
Against USD's 2.
Then you're going to get a failure because it can't write to the multi-region journal anymore. So it's going to kind of...
Consistent read. You said consistent read, right?
Yeah.
So if you do a consistent read in East 1, you're okay because you have access to the multi-region journal, but in East 2, if you try to do a consistent read, it'll say, I can't.
Yeah.
Okay.
That's also because you can't do a write in US East 2. And that means that a read is consistent because it can only be observed between US East 1 and US West 2 in this scenario. So here, that's why the read will work in US East 1.
But the super interesting scenario is a network partition between, let's say, US East 1 and US East 2. All things will work normally. You would be able to do strongly consistent reads, writes in all the regions. The only reason this is possible is because the replication logs would flow through US West 2 to US East 2 and vice versa. So because multi-region journal, US East 1 will be able to write to the multi-region journal, and that needs only 2 regions to commit. That's going to be able to use US West 2 to commit. And likewise, in US East 2, it is going to be able to use US West 2. So this is a slight difference. The regions will be still available. You can do strongly consistent reads and writes from all 3 regions. This is good. I'm going to skip this one. We talked about this one. I'm going to do a small demo. I'm going to see if I can switch over the screen and see if I can kind of change screens midstream. This is going to be interesting.
While you're setting up the demo, from the last slide, you talked about the different failure scenarios, but the latency is a question that I have. So, like, when in all these different, kind of all of these scenarios, under normal circumstances, how fast, like if you're in US East 1, with this setup right here, I would think that your reads and your writes probably can run in like 25 to 30 milliseconds because they probably don't, I don't know how it's set up internally, but I would think that like, you have 2 of your 3 regions 25 milliseconds apart, right? And so, your journal, I'm thinking is probably pretty fast, right?
Yes.
Okay, so without even knowing the ability to, so the problem is like all of your failure scenarios that impact anything on the East Coast, like, sure, it doesn't go down, but your latency probably spikes massively, doesn't it?
You're totally right. I think this is one of the things I was going to talk towards the end of the slide is multi-region is hard. It's not trivial, especially when you're kind of having an application stack which has to work across 2 different regions. Region failures can impact your stacks in very different ways. And this is one of the scenarios where all of a sudden, since your writes are slow and reads are slow, you will start needing probably need more compute to scale all of a sudden because now you're processing smaller number of requests and your throughput of your box itself has gone down, for example, right? So yes, this is something which we talked about last night as well. Like this is something we should talk about where multi-region is hard and the mindset you require when you're building an application stack which works across regions is going to also have to change a little bit because one, you need to be continuously testing this stuff where regions fail or there's one service which fails.
Do you have any way to, so that's a good point, you need to test this stuff, but like how do I test my application to know that it's going to work with like 90 millisecond latency? Do you have any way to inject latency
We, yes, that's also a very good question. AWS has come a long way. We kind of had where we didn't have this, but now we have experiments you can run, fault injection experiments you can run across multiple services. Dynamo is one of them. Dynamo Global Replication is also one of them, where we say, hey, you can pause replication so that you can pause replication. Definitely latency is one which we should have on our roadmap to add so that customers can experience this latency thing. And this did come up when we were building the fault injection simulator to say, hey, we kind of simulate faults today, but we don't simulate the latency. And this is one of the key callouts we had is like we don't simulate latency, but the idea was that we'll add a similar latency simulation later in faults. So
We did internal load testing for one of our internal services for a control plane system that we're building, and we know that for workloads that we have to put on this thing, we had to hit certain latency targets for the system to be able to stay up, and it's one of those things where if the database, I don't know.
if the database slows down, then
Numbers where if we're not going to hit these numbers, that control plane's not going to be able to handle the workload.
yeah. I agree. Let's see. Can I pull this one? No, did you?
Or just always use eventually consistent reads whenever possible.
Yeah.
That's the big thing.
ECU.
So I have an example. I just have a small demo here, which I usually give. The demo is 2 experiments. One is concurrent writes across multiple replicas in 3 different regions. I have a DynamoDB global table which spans 3 different regions now, has 3 different replicas. The table with the asynchronous, which is named async GT, is the asynchronous replication. So the first experiment I'm going to run is 5 iterations of counters, just running counters like, hey, increment your counter, conditionally increment your counter in each one of the regions. And we're going to see what the value and how the latency profile looks. My TypeScript is obviously horrible, so I didn't get this entirely correct. But as you can see, each one of the regions did its own conditional update, and the values are at the end, which you get displayed as basically whatever that region landed up writing. The latency was pretty quick, given the fact that I'm still talking from Seattle, the latency to PDX is quick. You can see CMH and IID matches the latencies. This is what Dynamo write latencies would look like. I have the average latencies was about 37 milliseconds to PDX, and IID was 139. I think this is mostly because of the client setup at this point in time, so the average is kind of high. But the key thing here is to notice that each one of the replicas got its own values, did its own update, and they all have converged on 5 at this point in time. So the writes locally were done even before they got replicated. So none of the other replicas even saw the value which what any of the replicas wrote before they did the increment. But the same experiment is very interesting to see. Let's reset the counter and run this experiment across a Mercy global table. It takes a longer time to finish running this experiment. And as you can see, the counter value is now 15 because I kind of incremented the counter 5 times from each of the regions. And the counter value is 15. The first update was in US East 2, 0 to 1. The second update was again in US East 2, but then US East 1 got its update through. But it took quite some time. It took around 408 milliseconds. It's just because if US East 1 tries to update and the update fails, you get a conflict exception, and that conflict exception is retried. So you can see that whenever it's getting a conflict exception, it's going to take a lot more time to kind of get the next update through. And finally, the value in US East 1 converges to 14 to 15. All 3 replicas would converge to 15. I should have done a read at the end, but I was lazy to kind of get that done. But but I have another experiment which actually does show how the reads work. In this experiment, what I did is that I wanted one replica to continuously write, and the other 2 replicas to continuously read the values of the DynamoDB table. So I chose to write to US East 1, and then asked US East 2 to do strongly consistent and eventually consistent reads. As you can see that when I did the writes to US East 1, I've been able to write to 5, and US West 2, after even 10 iterations for a second, it did not get the value 5, so the value 5 was not replicated here still. But US East 2 got the value of 5 replicated, so I was able to see the value of 5 in USES2. So you can see that when I'm reading from USES2 and US West 2, US West 2 doesn't get the latest write. So this is where the whole eventually consistent writes reads work for you, well, asynchronous replication work for you is kind of the thing with this one. And with Mercy global tables, I'm going to do a very similar experiment where I'm going to have one replica do 5 updates, and the other 2 replicas continuously read for a second to see what the values they see are. They're doing both strongly consistent and eventually consistent reads. You can see that US East 1 does apply up to 5, and both regions, good. Both regions are able to kind of, when they do a strongly consistent read, they get the latest value. The eventually consistent read, for example, in this case, did get a value which was local to a replica, which was not caught up to the leader or was not caught up to whatever the multi-region value was in US West 2. One of the replicas is lagging behind, but eventually they catch up to whatever the value is in US East 1. The latencies here, as you can see, for the strongly consistent reads are almost similar to the writes. And this is one of the key things we were talking about is a read gets converted to a write and requires the multi-region journal to kind of replicate that heartbeat, replicate the read barrier.
I have one question. What is the difference between consistently strong value and consistently eventual value, and why it is coming like alternate?
Because I issue both to the same replica and say, okay, fine, give me an eventually consistent value and give me a strongly consistent value, right?
So every second? So every second?
Yes, every iteration I do that. And you can see that.
But in the US West 2, the things are a bit different, right?
Yes, this one was different.
Oh,
4 and 3.
sort of similar. Like every time you have
Every time I give a strongly consistent read that goes to the leader in that particular region and say write a read barrier and then give me the value. They eventually consistent like give me the value, first value you get out of the first replica, right? So the value was not updated in that replica, so just return back 3. This experiment works sometimes well, sometimes all of a sudden eventually consistent gives the same value as strongly consistent, like for this region. So it's nice that I got a difference here today, like where I could show you guys what is happening. Having said that, let's go back. Right. This is a matrix of difference between asynchronous global tables and multi-region strongly consistent global tables. I won't kind of bug you with this. I think the key differences is the network isolation and network partition and how both these tables behave, and that might be the only thing which is very different between both of them. And then the latencies. The thing I wanted to kind of get is like multi-region mindset, which is something which is very different from a regional mindset, because in a regional mindset everything is almost constant and everything is almost predictable. In a multi-region, it's kind of the mindset itself is hard. You kind of have to kind of think about how you're planning to use multi-region. How are you kind of going to test this always? How does your restore, like for example, if you're using backups, restore from your backups regularly, fail back, fail over, because you need to know when you want to kind of fail over to another region whether everything is working, your credentials are working, or every other system is working, because it's just not going to be one part of the service which fails. When I think about multi-region, it's just not about like, hey, is a customer going to flip over just the DynamoDB, right, reads and writes? I think about an entire stack switching from one region to another region, because most customer stacks work within a region very well. It's isolated to a single account, and it's better. The other thing is test system invariance. We place a lot of emphasis within Dynamo replication and storage to test the system invariance and correctness and availability overall within the storage area and the replication area. This has helped us a lot. We use TLA Plus and formal monitoring tools like P to kind of constantly check the correctness of the system. When Akshat and I were working on transactions, we built a transaction acidity verifier which continuously takes the replication logs and verifies whether every transaction meets all the system invariants we kind of set for it. We also think about systems, when we build systems, we think about systems which we would drive developers to use it as an active design, because pushing the big red button is a once in a lifetime thing or once in a decade thing, whichever way you want to look at it. But that day it should be easy for us to push the red button, and it's easy if it's an active system, because then you don't really have to worry about like, hey, if I fail over to another region, whether it's going to work or not work, right? So the multi-region mindset is super critical for anybody who's like developing multi-region applications or multi-region services. That's all I had. If anybody's interested in P modeling or P checking, P observe, which we use today to model our replication protocols and verify its correctness continuously, I think you guys should kind of check out P. P is really useful. The nice thing about P is that it lets you take it keeps your code almost identical to what your production code is going to be. No, not Rust code. Rust has a different checker. I can put you in touch with that. But at least for Java and a bunch of other programming languages, P is really good. It lets you kind of keep your code almost close to what it would look like. P observe is another tool which basically lets you kind of check the logs and check correctness just using application logs. So you don't have to worry about writing the invariants in code. And that's all I had. Either it was super hand wavy or
I could throw one question at you. Your replication conflict exception.
Just a minute.
Sorry. For replication conflict exception, I think was close to what it was called. Do you throw that for any conflict at all? Like, for example, an increment. Like if you're just trying to increase the value of a number by 1.
Yes. We do throw a replicated write conflict exception for any 2 concurrent writes happening to the replication log. We could have optimized it for condition check, saying, hey, condition check failed. We thought it's simpler to kind of implement replicated write conflict exception back if we see 2 concurrent writes.
Is that true also even for operations like trying to put an extra element into a set or something, a string set? You could imagine that they don't conflict semantically and that they would converge in either order.
Yes. So both DynamoDB global tables do state replication and not operation replication, just because it confuses. When you want to replay it, it's very confusing. If you're trying to replay operations, you exactly have to replay all the operations to get to the current state. It's easier to do state replication and have the state replicated. So yes, if you're adding an element to the set, it's a different state. And if you're adding the element to this set, it's different. Though I think in Synchrona, we did solve the problem using CRDTs, which I think is cool. And I think Dynamo should, at some point in time, implement CRDTs, and that's easier to do that. Yes, I think that's a good idea.
Can you go back to that heartbeat read slide? So where we are writing to the multi-region journal and then you fired a heartbeat.
This one.
The screen is different.
Oh, screen is different. Okay. Play from current slide. Good job.
Oh, yeah. So if I understand this correctly, so you fire a write A in this case, right? First in region 1. And that write A goes to multi-region journal, and then multi-region journal fires a callback to all regions saying that apply A.
Yes.
And then when the consistent read comes to region 2, what is the exact sequence of steps? Like it triggers a heartbeat to the multi-region journal first.
Yes.
And then what is the sequence of steps after that?
So it triggers the heartbeat down to region multi-region multi-region journal, which the listener in region R2 has to pick. Right? But the listener in R2 can only pick that heartbeat if it's applied all the writes before that. It cannot deliver that. It's doing all the delivery of all the logs which are appended in serial in which it listens, it gets the callbacks in, right? So it would get apply A. If it's not got an apply A yet, it'll do the apply of A first, right? And then it would say, hey, heartbeat, it's your turn to read the item. Now you're good to go read the item. And you can now go to the leader to read the item.
So a couple of questions in that. So how does it know it is apply A or apply B it has to look for? Is there a hash-based search?
No, it doesn't. It doesn't care. You might have not even written to the item the consistent read is reading, right? But to just maintain correctness, it has to apply all the logs to know that there's nothing there. It has to apply everything to all the items even before it does. You may be doing consistent read. Do a read barrier like.
Back, and then it'll say that, okay, you're ready to read. What happens to the client during that time? Like client receives.
Client is waiting. That's why it takes like 200 milliseconds or like 80, 90 milliseconds. Like most of the times when you do a consistent read, the difference between a consistent read and a write, the latency is not much. Like especially if it's like a 1 kilobyte read and write, it is hardly anything because the heartbeat has to circulate through the multi-region journal and you pay that cost. We could have switched very easily to what the protocol is. So when we built this protocol, we did give leeway to build a zero RTT read, where you can do the local read consistently and hold on to the commit, just like what DSQL does, where DSQL says, hey, commit this in future, and I'll make the read wait until that timestamp and make sure I've caught up to all the commits. It's not very hard for Dynamo's protocol to change, but we thought, okay, this is a better thing for our customer experience overall to kind of have reads be the same latency profile as writes. And customers are all over the place as far as if you ask them like, hey, what read and write latency profile you want? It's like they all wanted strongly consistent reads.
How does it even know it needs to do the heartbeat, or does it do for every read?
It does for the strongly consistent reads. So if you issue a strongly consistent read, you get item and you set the flag saying, hey, I want a strongly consistent read.
Even in R3, it would do the heartbeat to get the latest ones.
RT would also listen to the heartbeat. It will ignore the heartbeat. It will say, hey, this heartbeat doesn't belong to me, and it will ignore it completely. So yes, you're right. The heartbeat is also a callback to all three regions because it's written to the journal. The journal doesn't know what is being written to it. The heartbeat is just a record in the journal, like saying that, hey, this is a read barrier. It's a read barrier for a particular read in region 2 in this case, right? So R2 would get it and ignore that record completely and say, hey, I don't have anything to do with this record. It's split between all three regions, R1, R2, R3.
So what happens if one of the region goes out? The whole journal is gone?
No, the other two regions will be still good enough to do a commit.
So they can execute all of them?
Yes.
As long as 2 are alive, it still works.
Yes.
Do you do kind of like coalescing of writes in the journal?
No, not now. It's something which we always kind of thought whether we should be doing coalescing of writes across in the journal to just increase the throughput. But we not found any much performance gain of coalescing writes. If at all anything, we may land up taking a latency hit because then you have to pick up the entire log, write everything in the batch across multiple keys, and then return a success to the customer. So every write is its own log entry in the journal. And that also helps us kind of use the journal later if you want to kind of replay the entire set of sequences to another database.
Right, but like, I think I meant like journal can keep all the entries which were written, but when sending the apply to R2,
Yeah. No, journal doesn't do that. Journal always gives a callback for every record because it assumes that every log entry is separate by itself. So it just gives a callback for every entry. There's a sequence number attached to it. There's a bunch of things which are attached to it. It's individual to that particular log entry.
And is there by any chance, like, this is just a hypothetical scenario, but like one of the apply could drop, then like by sending from journal to R2, if you send like, oh, there are 10 different apply which you need to do for A, and one of them gets dropped or something, like, is there a way to do some kind of verification of?
This is Akshat's favorite topic, so I'm going to say yes. I think one of the things we land up doing across all global tables is run anti-entropy in the background all the time to quickly detect any convergence which are not happening between the three replicas. And this one is even more serious because if the apply A gets dropped, then everything else is going to kind of stop working after that. So yes, we continuously keep checking all three replicas for convergence.
Thanks.
Is there a limit on how many regions it can work?
Mostly global tables, now 3. Asynchronous global tables, all regions within a classic partition, you can just add a replica. It's just a lot of writes, but there's no limitation on how many regions you can have.
So I have a question. If things started to lag, sure. If things were starting to lag, it seems like that would be bad. Especially like with I mean, even your reads are going to start to just you'll see latency, right? Latency on your reads and your writes. What do you do about that? I mean, and there's a couple, like you could have one region, I don't know, it depends what's going on. Like if the multi-region journal seems to get kind of clogged up a little bit, it could affect everything. It could maybe just be the, like one region getting stuck somehow. I mean, to some extent, we're just like trusting you guys, but also like we care a lot if our latencies start to go up, and are interested to kind of know like what are the bounds, what kind of expectations should we set for like tail latencies on these reads and writes, that kind of thing.
The tail latency is a very tricky one, especially with multi-region global tables, which strongly consistent, just because you need 2 regions, and like you said, UOCs 1, UOCs 2 is like 20, 30 milliseconds regularly, but once in a while you'll see a blip of 200 milliseconds just happening just that way. Right?
Mm-hmm.
We closely monitor it to make sure that it's not a sustained event and it's just a blip in one or two operations where the tail latencies go high. So we do closely monitor it. Definitely we could kind of move the read protocol away from the heart beating so that read is like way faster than what the write is.
What about like non-network issues though? Like, so internet fine, like I get that, that's easy. That's totally expected because like I've sent lots of traffic across the country. But like, what about other things like whether it's, I don't know, operational stuff, whether it's just like a noisy neighbor or somebody just jams a bunch of traffic in, or a deployment that goes south, right? Like somebody deploys something, some code, and it just like wasn't perfect and there was a little tiny glitch. That's probably going to be your one of your most common things,
So I think we've kind of have the bells and whistles for monitoring deployments, making sure deployments don't lead to glitches, like a bunch of the things, like even when we do the front-end router deployments, we drain all the traffic before we do that. If you're deploying, we usually don't. This is one of the things we talked about as the multi-region mindset, right? How do you think of deployment across regions, right? Because now it's not that the customer is just dependent on that one region and one availability zone deployment, it's cross-region deployments as well. And there's a lot of emphasis placed on like, hey, if IID, PDX, and CMH are your core regions for a multi-region global table, or most of your customers are using within the US that global, then you deploy to CMH, wait for CMH to kind of stabilize over a period of time. You can go deploy some other region because you kind of stripe regions in that way, as opposed to saying, okay, after CMH you can go deploy to IID. No, there's a lot of emphasis placed on like how are you deploying to the stacks now, right? Especially we don't want to take down like. If IDPDX and CMH are like dependent regions, we don't want to kind of take down 2 because we need at least 2 regions to have the commits happen.
It's about lower, I would say it's about fewer assumptions. Even in single region, you can make some assumptions. In multi-region, you have fewer assumptions now, right? So,
I mean, I wasn't so much thinking like a tail latency that goes from 90 milliseconds to 500 milliseconds. It was more like, just like,
A bigger problem,
database
sustained.
lags. I've seen, not in the context of this, but like in the context of say Postgres, like I've seen replicas lag by a lot, right? And just for various reasons. And so like replication lag is a thing that's kind of always in the back of my head. Like, can that be a problem one way or another?
We like even in Dynamo, I think when Dynamo regional, we keep track of how far behind a replica is, and we usually get, that's part of the work that Pratik did, is like we usually kind of cut loose those replicas and create a new replica. We don't really care about, we can go debug why the replica was slow, but we can, if we cut loose and add.
24-hour cutoff, so you clearly had people who were like, had something lagging over 24 hours at some point.
but that was customer induced.
That was customer, so sometimes customers would yank the encryption keys because they thought the policy is not required by Dynamo to replicate.
Yeah, that's right. Yeah.
Yeah. I think, but to that question, I think there is like solid monitoring behind, like phases people or phases operators or triggers automated to fix that.
said choose or There's the question. It was what you
So I'm kind of curious from like a deployment and testing perspective, because you're deploying you're deploying to like different regions, right? And so at different times. So how do you sort of model like version inconsistencies, or is your protocol just like stable?
So a lot of this is baked into the design of the protocol itself. Like when you think about the protocol, we think about like, hey, how do we make sure that its protocol is upgrade safe?
Like first-class citizen.
Yes, right. For example, if there's a change in the write schema, then we would kind of make sure the readers are running up and front before the write is done. Even when we're building transactions, this is one of the key things. Is like our protocol is upgrade safe because it's very localized to the transaction coordinators and what the storage nodes talk about, like whether they say yes or no. There may be an availability impact, but correctness is of paramount importance for us, so we always kind of bake that into whatever protocol we're designing.
This looks like more like Paxos, right? I don't see any difference.
The multi-region journal is a variant of Paxos. So was Dynamo regional replication is a variant of Paxos. So what multi-region journal does under the covers is a variant of Paxos. That is, no questions asked about that. But Dynamo itself is just using the multi-region journal. It's just doing deterministic execution on top of that. So,
Like C reads are basically going through Paxos.
To the journal, yes. It's like basically a read fence saying, hey, I want to read, but I want to read all the writes before this fence.
Why can't like multi-region journal, when the nodes get the updates, do they just give it to the data nodes from the same region?
No, it's just an abstraction on top of it, right? They don't know that who's doing the writes. This goes back to like how do you think about like protocol version update and everything else. Like they don't know about the storage nodes or anything, and the storage nodes in two different regions can have two different set of keys. So the GT shard process is just a compute node on top. It says, okay, when I get a write or I get a read, I will convert that and write it to the journal. So the journal can independently scale from the storage nodes and the compute nodes overall. So. Good, thanks. Thanks, guys.
Want to say goodbye, maybe?